All right, thank you, Massimo, and thanks to the organizers for bringing us together in this wonderful, unusual location, at least for physics conference. It's a pleasure to tell you a little bit about some recent highlights on large-scale quantum simulations using cold atoms, but since not everybody is really used to the field, I give a little bit more general perspective, but also give some recent detailed results. So I think, as was alluded to already before, I think it's a wonderful time for scientists, maybe for business applications, we still have to wait. Hopefully they will come. But at least already now for scientists, it's a wonderful time because with these machines that we have available right now, either the quantum computers or quantum simulators, and there's such a big difference at the moment, I would say even, we have a wonderful time learning about quantum many-body systems in new ways, very much in the spirit, of course, what Richard Feynman was putting forward. And indeed, as was mentioned already by Randy, I think this goes back to the early proposal by Peter and Ignacio in 1998, where they really for the first time pointed out how you could use these artificial systems concretely to simulate physics, for example, of strongly correlated electron physics in these extremely dilute gases. And we're celebrating 25 years of that proposal. And last year we had 20 years of the experimental realization, where Marcus and I wrote a short piece on that in Nature Review Physics. And I think now what's really remarkable that this whole theme of quantum simulation has really become one of the most dominant fields, most dominant application fields across platforms right now. I would even argue it's one of the most impactful applications that we do have right now in studying using these quantum systems for these quantum simulation approaches. So the system we use are these ultra-cold atoms and lattices, and here you see a very nice picture of such an optical lattice from Ted Henge in Munich, where he just interfered 5 laser beams, and you get this beautiful quasi-crystal interference pattern that you see here. No calculation, really recorded optical light field in which we can load, bosons, fermions, spin systems. We can lock the systems into this array. We can have them move. And I think the big strength of this platform is that we can put fermions in there. I think there's only the quantum dot platform which can do similar things, so we can really naturally simulate the physics of strongly correlated electron systems without any overhead in the mapping of those systems. So for some time, you get some parameters of these lattices I've drawn out here. We thought that each time we want to make a new lattice, square lattice, hexagonal lattice, triangular, and so forth, we needed to, we can do it in principle, but in practice, it would mean that we would have to rearrange our whole configuration of laser systems in the lab. And okay, that's, as a supervisor, easy to say, but the graduate students will not be very happy with you when you tell them to do that. That means months of work, reconfiguring the system. I think really a breakthrough, we recently had a proposal, found out a way how we can do that actually without any reconfiguration of the system. Within one experimental sit-up, you can blend over between these different lattice configurations, square, hexagonal, triangular, Kagome, leap lattices. And that's, of course, a tremendous advantage now in terms of programmability of these systems. As for interactions, there's quite a few interactions you can use in these systems. Mostly we're using here collisional interactions, but you can have dipolar magnetic, Rydberg interactions, or you can have all-to-all interactions, for example, if you place these atoms in cavities. Now, one thing, of course, that's for us been really motivating is to build a system, build an experiment where we can really observe, I would say, this more prosaic formulation here, the dance of the electrons inside a material. Can we take photos of electrons inside a material and really observe electron for electron what's going inside this material? That's been the spirit. But to get closer to that goal, this technique of quantum gas microscopy was developed in Harvard and Marcus Group and our team in Munich, and now established in many other labs, such as Martin's lab at MIT also, or Wasim's lab in Princeton, where you can get pictures like this one, which shows you a beautiful image of thousands of atoms in this optical lattice, where each of those bright spots is basically a single atom that you detect with high fidelity in those lattices. So it's really this dream of imaging each electron in a solid becomes true here, where you image each individual atom, state resolved, double-on holes you can resolve in this way with a little bit more sophisticated measures with very high fidelity. And that's, of course, now really wonderful from a quantum point of view, because if you have a quantum state you're interested in analyzing, getting those snapshots of the wave function basically means you can get probability distributions of configurations, and from these probability distributions of individual configurations that occur in your many-body system, you can actually calculate things like correlation functions that you can then test against theory. So here's just some examples of what we can do right now. We can work with a few thousands of atom systems, up to maybe 5,000 atoms in this mod insulating regime, as was mentioned before, with fillings around 98%. In the better cases, we can use different lattice geometries. As I told you, we can do different terminations to also determine whether we are studying topological systems or non-topological systems in this way. And of course, the one problem, that comes to mind, I think that's a good benchmark problem for all, basically, quantum computers, simulators. We need these common problems to test ourselves on. And a good common problem that is, of course, also of economical relevance and is scientifically interesting is the one of the Fermi-Hubbard model, of course. And Randy put up the phase diagram already. You see in the cuprates for undoped systems, you have the antiferromagnetic phase. And then as you dope the system, all these interesting phases appear. And if you ask what is the physics question that is determining here this interesting behavior, it's actually very simple interplay of things. It's actually the questions of holes that want to delocalize, hole dopants that want to increase their kinetic and minimize their kinetic energy by moving around. How is that competing with the tendency of the system, the background of the system, to be magnetically ordered? And there, of course, this idea of quantum simulation is now fantastic because we can look into this system with very nice ways. So here's a picture of how we do that actually in the experiment. So on the upper right, you see how the trap is actually shaped. We have a lattice in the central region connected to a reservoir that allows us to prepare rather cold samples in the system. You see the density in the graph on the right. You see how you get this really nice mod insulating density in the core of the system. That's the physical system we're looking at. And if you do a spin resolve detection and look for the spin-spin correlations in the system, you can see this, measure this via the spin-spin correlation function. That's the map you can see on the left. And you can see that you basically get antiferromagnetic order across the entire system. And now you can go to theory. For example, you can go to people in quantum Monte Carlo, like Lode Pollet in Munich, and you can lay on top of that data the quantum Monte Carlo curve, which is the blue curve, and you can see it matches really nicely, and we can get very precise estimates of the temperature. This quantum Monte Carlo, I should say, works nicely in the undoped regime and for slight doping, but once you go at these temperatures above 10–15% doping, then already you have a problem in running this quantum Monte Carlo, and quantum Monte Carlo doesn't work anymore. So one thing that's interesting, if you look at the physics, what's happening in these systems, if you have these holes moving around in this antiferromagnetic background, is that when a hole moves, and you can see that from the left to the right, it actually tends to destroy the antiferromagnetic background. And so the more it moves, the more it destroys the background, and that costs a lot of magnetic energy. So there's actually a linear confining potential connected between the hole and the flipped spins it leaves behind, which increases linear in energy as a function of separation of the hole from this phenon tail that it leaves behind. And this actually looks very much similar to what you have in nuclear physics to partons, where you have confinement in the system, and very much like that, you can think of these particles that emerge here as partons in nuclear physics, new quasi-particles that emerge that in this context, in the condensed matter context, are called these magnetic polarons. And now we can take, for the first time, real pictures, using this data, real quantitative pictures that we can compare to experiments from these polarons. In this picture, you can see in the middle the dopant. In this case, it was a doublon. You could think about it as a hole also. And then you're plotting surrounding this mobile dopant. You're looking at how are the spin-spin correlations distorted relative to the background spin-spin correlations without the dopant. So this red and bonds or blue bonds indicate the strength of the spin distortion around that mobile dopant that you have in the system. That gives you a very, very nice quantitative result and a first picture ever of such a polaron in real space. And you can think of this object, if it moves around in your material, really it always has to drag around with it the spin distortion in the system. I should say there's very nice work very recently in Marco's group and Wasim Bakar's group on showing how a different mechanism for polaron formation occurs in frustrated system. It's basically kinetic magnetism that plays a role here, but which gives very similar pictures to the one that I showed you here before here. So one thing I want to say, can we really predict new phenomena? Can this really be useful for materials? Actually, I want to show you an example which we found out recently. We made a proposal by understanding this system better, how you could boost the pairing energy by amount of 15, by almost over an order of magnitude. in the system, and by basically going to so-called mixed dimensional setups where holes can only move in a certain dimensional restricted geometry, but spins can interact in a higher dimensional background. And by showing that, we could indeed show that this boosts the pairing energy, and very recently we can also use this to see something like stripe formation in the system, where you go beyond simple pairing of those holes to the observation of these extended density structures that were known from the ITC community as stripes in this phenomena. Now, there was very recently also this year, there was prediction for a new superconductor, which made a lot of splash actually. It's not LK99, so you heard about that one, but that's not about what I'm talking here. This is the nickelate superconductors, high TC superconductors, which people are very excited about. And in Nature, it even made it to this accelerated article preview. I don't even know what that is. So anyway, the theorists looked at that, and they found actually in these nickelates, you have exactly this new pairing mechanism at hand that works out in this mixed dimensional geometry, and the high TC temperature is very likely due to this mixed dimensional geometry that's also occurring there. And I think it's a very nice example of something that was, now for the first time predicted in the cold atom setup, and now finds its applications in the materials. I'd also like to highlight very nice work from Martin's group. I think, Martin, you're going to talk about that probably on the attractive interaction side, how that's connected to BCS physics, and also from Marco's group on looking at these frustrated systems. As I showed you, if you now tune continuously the lattice structure from a system without frustration to a system with frustration, you can really continuously track in a very quantitative way with very quantitative results. You can track how these spin correlations evolve. So we're now in a very exciting time, I think, in this field where we are getting to temperatures which fall within this so-called pseudo gap regime. And for those who've worked in high TCs, this pseudo gap regime is clouded with mystery. I mean, there are thousands of papers on this pseudo gap regime, what it actually is, what's the physics behind it. And I think we can now, have a unique opportunity to look into this pseudo gap regimes with the new tools. And just 10 days ago, we had Subir Sachdev visiting us at MPQ, and he was very excited about these new real space pictures that we can have, that we can maybe, learn more about this phase, because maybe the conjecture is that the reason we understand this phase so poorly is because we've always been looking with the eye of two-point correlation functions that are accessible to condensed matter probes at this phase. But to understand it truly, what lies at the heart of this phase, we might need to look at higher order correlation functions to understand it. And of course, here, these systems have a wonderful, maybe new possibility to address this problem. Massimo, how am I doing in time? Did you check? Okay, well, wonderful. So I can actually then go slow a bit down even, okay, and tell a little bit about other fields, just a few highlights where there's been impact and where I think, and tell you an outlook, what I think is interesting for the future. So dynamics is interesting in these quantum simulators because it's naturally the one application where we very easily come into the regime of quantum advantage or something, or at least that's hard to calculate on any numerical algorithm. And one of these early experiments going back to that really goes to this foundational theory proposal from Lieb and Robinson, how information spreads in many body systems in the 70s. And I think it really was a foresight paper because it really already pointed the path how important the marriage of information science with quantum physics was going to be. So that was actually measured for the first time in the cold atom setting, that you have a light cone-like spreading of correlations. Later on, there were these beautiful experiments in ion traps looking how that's modified in more long-range interacting setups. Then there was questions on fundamental physics questions on thermalization, how to measure entanglement entropy. And here, Marcus and his team really did beautiful experiments based on theory by Peter and his group and Dieter Jaksch on earlier work on how to measure this entanglement entropy using basically a Hong-Ou-Mandel many-body experiment that you could do in those systems. Then we can look at phenomena and dynamics connected to dynamics also on localization in many-body systems. This is a difficult topic of where you need long evolution times in the system to say definitely what's going to happen. And I think the experiments have shed some light on this, although I think the whole topic is not completely concluded. Or, as another example, just to show you there's new spin transport, universality classes in spin transport emerging that people have thought about or had been discovering just a few years ago that could be proven now in these cold atom settings. And the nice thing is, as you can see in the picture on this graph 4, we can prepare systems like this domain wall, and we can study atom by atom or spin by spin how this domain wall gets dissolved. And this is a single snapshot, and in another snapshot, you would see a different picture of spins. And that basically means if you take thousands of those snapshots, you can measure what is known as the full counting statistics of this transport. So you can measure not only the mean, you can measure the fluctuations, you can measure the skewness, the kurtosis, the higher order moments of the distribution, which give you a wealth of new information about transport phenomena that were simply not accessible before. So where are we heading next? What should we look at? I mean, we've seen already, and we're going to hear a lot more about, I think, this analog mode of doing things. Then there's the digital circuit mode, and they seem to stand a little bit apart. I don't think they're so far apart. I would even argue everything is analog so far. Even in a digital system, you're just pulsing, basically, right? As long as there's no full error correction, everything is analog. But I do think that marrying these concepts of digital with analog, at least for the near future, is going to be very exciting because it gives us a lot of new possibilities to study those systems. And in the context of these systems I showed you here, we can really think of orbital Bloch spheres, orbital qubit states, which I've just mapped out here in the double well system, where you have the populations in the vertical directions. On the x-axis, you would have maybe the currents, and on the y-axis, the kinetic energy. And we're learning how to measure these now in the experiment, and also maybe how to control them at the local level. And I think this will give rise to new forms of quantum computing, quantum simulation, where we can really harness also this fermionic statistics. And there's a very nice paper from Peter's group, and actually June was also involved, I think Misha also, where this was actually laid out here in this PNAS paper. So where are people going in the cold atom community? Just a few things I find very exciting. There's, on the one hand, there's really a remarkable work coming out of Zhan Weipan's team in Shanghai, in China in general, on how to control the entanglement, how to control these many body systems with completely new degrees. I think we found it extremely exciting that these polar molecules are now becoming extremely interesting in the past years due to the pioneering work of Debbie and June, who started this whole field. But now we're learning how to really cool them to quantum degeneracy, how to learn about new scattering resonances that were predicted more than 20 years ago by John Bohn, realized them in the lab, where we now, I think, for the first time have the prospect that we can look for fermionic superfluids, P-wave superfluids. We're not far away from that. The T over TF we reach in the lab right now is 0.3. And around 0.2 T over TF, you expect these P-wave superfluids to form. If we do that in 2D, you have topological superfluids, P-wave superfluids, and if you can now marry them with this quantum gas microscopy method, you can see the potential of all of that. I think very exciting is the last thing. I think something that Adam Kaufman in Boulder has been pioneering is this marriage of the beautiful tweezer world with the optical lattices. And just to show you just the picture from our lab where we hope where this can go, is the picture of these atoms in the lattice of tens of thousands of lattice sites populated by single atoms. And now you can marry that with the tweezer world and move atoms around, shuffle them around in the lattices to generate more complex initial states and use these digital operations to learn more about these systems. So I think it's a very exciting time. I hope I'm just on time, Massimo. And I thank you very much for your attention.